Okay, let's continue part 14. We continue on electronegativity and the bonding polarity. Alright, part 3. We have two parts. We ended up with introduction of covalent bond. We talked about covalent bond. Let's just have a small review. We use hydrogen gas, diatomic hydrogen gas molecule as an example to describe the stability of the bonding, the single bond, sigma bond. When these two atoms of the same element, hydrogen, getting close enough, and how the energy in the whole system decreases and they get more stability, and that kind of a situation for these two atoms, they're not existing in nature by single atoms of hydrogen itself. But when they form a diatomic molecules, they are more stable because the energy level for the whole system with two atoms will be lower than single one. That's what happens when they are too far away from each other and getting close. And the intermolecular distance is so big, there's no repulsion or attractions between those nuclei and the electron and so they have energy, let's consider as zero if we have this in nature. But then when they're getting close enough, push towards each other and then getting close, they actually lower the energy level for the two in one system. And then until to the bottom of a certain distance, that's about 0.074 nanometers, it's about 0.7 angstrom. And that's the distance. When they form a sigma bond, overlap the electron clouds from both atoms, and had one clockwise, the other was counterclockwise, opposite self-spin electron getting close enough to form a bonding. They literally lower the energy for the entire system. Then form a bonding. These two atoms getting together, but getting a diatomic molecule is much more stable than individually separated in nature. So that's why they form a diatomic molecule was preferred in nature. But if you push these two nuclei with the electron 100% shared in the middle, we call covalent bond. Then the repulsion between these two nuclei getting greater and greater. So that time the energy actually for the whole system going for the lower possible stage and getting higher and higher. In other words, the repulsion, generates the energy, so it's a little high for the system, so they are unstable. That's why the energy level goes high when they get too close and is too short than 0.7 angstrom or 0.074 nanometer. Then that is not stable. So the best way is about 0.7 angstrom. That's the length of the sigma bond between two nuclei of two atoms from hydrogen, form a diatomic hydrogen gas molecule. Is that clear? So that is the situation we call 100% covalent bond, because neither nuclei or neither atoms is stronger than the other because they are identical from the same elements. They try to compete for the bonding electrons, right? Only one each, correct? There are two electrons forming a single bond from the two atoms of hydrogen. But then the competition can never end because they are identical. Nobody can win. Nobody is stronger than the other. Finally, they have to have a summit. Let's say not fight. Let's just put these two electrons form a bond in the middle of our distance. And that is where exactly the same distance to my nucleus, also to your nucleus, and the same distance to both nuclei, and then that's the lengths we call the bonding lengths belong to the diatomic molecule of hydrogen gas. Then that is covalent. That's 100% shared, because why? Both are identical. Nobody is stronger than the other to pull the bonding electron towards itself, so it will be shared right in the middle, the same distance between each. So that's 100% sharing covalent bond. Now, when we talk covalent, this term comes from a valent plus a CO, right? Co means something coexistent, right? cooperate, and then mutually. So covalent means the bonding electrons, these two, will be both covalent to both nuclei. Does it make sense? So it should make sense, right? So one of those two is from one hydrogen atom, the other one from another hydrogen atom. They always spin around, and then they spin so far away from the nucleus, and then interact with another electron from another hydrogen atom, right? They form bonding. But then we call them valence electron because why they are able to form chemical bonding compound, and form chemical bonding in the molecule, and that's interaction, right? Chemical reaction. So they form molecules. That is called valence electron to form bonding, form chemical bonding. But covalent means what? Covalent means they both, the covalent bonding is the bonding electron belongs to both nuclei, right? So that's called 100% shear, right? That's the situation. Then the first type we talk about ionic, of course, that the bonding electron are completely transferred from one atom to the other because the other is an electronegative element, has higher or stronger electron affinity during the bonding formation when the two electrons getting in the middle of the nuclei, and then that one is more electronegative type of elements belong to the non-metal category in the upper right corner on the periodic table. Those elements, we call them electronegative elements. And on the left-hand side, all the way to the left, and almost 3/4 of the elements out of this 120 elements total, and those are metals. They are considered as electropositive elements. They tend to be easy to lose their electron to the electronegative elements. So in that case, those electropositive elements tend to lose their electron, right? And then to who? To those electronegative elements, then electron transfer is occurred. And then electron transfer from electropositive elements to the electronegative elements, then that is called ionic bond because during the bonding formation, that particular electron join the electron orbital, the outskirt covalent electron orbital, very outside outreach, right? And then belong to another electronegative elements, form a bonding. That case we call ionic bond, right? Ionic bond. Now then these are two extremes. What would be in the middle? Or kind of a moderate. Yeah, we have the third kind, that is what we talk about, is called a polar covalent bond. Now, the definition here is very simple. The bonding electrons, which are two, are unequally shared by the two atoms. Now, we talk about a covalent bond, or 100% covalent. Right here, in this case, these two bonding electrons will be 100% shared, belong to two nuclei of hydrogen atoms, right? But in this case, the partial covalent bond is not going to happen between two atoms out of the exact same atom. It's going to be the two atoms out of two different elements, right? Is that right? If it's the exactly same elements, will be identical, will be 100% covalent. But he said polar. Polar means what? Polar covalent bond is not completely shear. So apparently, one side of the bonding seems to have a little bit more stronger negative charge to nature than the other side. So that is the covalent. Covalent bond is supposed to be equally. Both sides should be, no difference, right? But the polar covalent bond will show a slightly difference in the charge. It's called a fractional charge. Now, this case is considered as unequally shared by two atoms from two different elements. Now, what are those? Those were most cases, including hydrogen, because look at this periodic table on the train of electronegativity. Now, those were the non-metals. They basically very close to each other in their value of electronegativity. Now, when we talk about ionic bonding, we use sodium chloride. Now, check the electronegativity value for sodium and chloride. Sodium is 0.9. Chloride is 3.0. The difference between them is 2.1. Now here, of course, hydrogen 2.1 and another hydrogen also 2.1. So difference for the electronegativity between these two hydrogen atoms is going to be 0, right? Same thing. So, but here, so what happened is you have more, the bigger the difference between the electronegativity belong to two atoms out of two different elements, the more possible to form ionic bonding. The closer, the smaller the difference of electronegativity value between the atoms of two different elements, were largely possible to form polar covalent bond until they are exactly identical, become totally 100% covalent. Is that clear? So we have a difference, we have a distribution of what? Of the difference between the electronegativity value for two atoms. So only if they are same elements, the atom belongs to the same elements, right? They will be 100% covalent. Otherwise, belong to different elements, they either polar covalent or they are ionic bonds, right? So let's see, if we have a compound, right, and it's formed from hydrogen and fluorine, all right? So example, right, example. Who's dead? Oh, it's dry, it's brand new. Okay, so a binary compound is composed of the atom of hydrogen and an atom of fluorine. H and F, right? You form bonding in between, all right? Now, so check the difference. The difference for the electronegativity, right? Fluorine for F is 4.1 in my table. Most of them 4.0, all right? I use the old book, maybe. I'm old enough. So, and then minus what? Minus the the difference. That's not F. So 4.1, and then minus the value for the electronegativity value for what? Let's see, H and F right here, and the 4.1 F, and H is 2.1. So the difference is 2. All right, difference 2. Now, 2, actually, the difference for electronegativity value for two atoms out of two different elements, if the difference is only 2, it is the beginning that just started, right? Just started, right? Touch a little bit about ionic, but still close to, you know, close to have a feature of covalent. So 2.0. So it is not, let's put it here, it is just the beginning value of difference of a kind that can be considered as ionic. Alright? Not very ionic. Alright? The difference. So what happens actually, we are able to test it. If this is covalent, it should not appear in the electric field to have a attraction towards the electrical positive or electronegative polarity, the field. But if you put this element, this compound into the electric field, so what happens is if you have if we apply the electric field to the HF molecules in gas, that's gas phase, let's say, in molecules, the randomly moving around, random moving HF molecules will align up along with the electric field. So what is the situation? So if you have those HF right here, and then this one is FH right here, and then this one is FH this way, and you have three of them, and you have another one, it's like a HF this way, and then you put this whole thing, this whole gas, and into the field, electric field. Say here is the positive and the field, and this is negative field, and you passing through, and then they all become what? Become this edge. This edge is slightly positive, so the edge become like this. They all line up like this, and the F seems to be, this is the way supposed to be, has a positive end of this molecule, and this is the negative end of the molecule. It seems to be slightly the no, this is positive end, this is negative end. Let me reverse it. So just put this field. Yeah, they all just look like this. So you should have, this is the positive end, this is the negative end, and the same thing. So here is same thing. Negative end, positive end. Okay. And then positive attracted by negative, negative attracted by the positive. So there's one more, so let's put this one here. So you have another HF, and then it seems to be, this end is positive, slightly positive, this end is slightly negative. So we use what? We use this to represent HF become a polar covalent bond, with this end is slightly positive, is on this side, and this end is slightly negative on this side. So we put sign delta, italic delta, positive, slightly positive, delta negative. I'm sorry, this is look like a duck. All right, that's slightly negative. All right. So this is the polar covalent bond between the hydrogen and the fluorine. Now, from now we have all three type of bonding we introduced and we covered. And then what is the best way to make a judgment? What is the bond belong to? What is reliable reasoning resource we can rely on to say, okay, if this is this, and then this is such, and then that must be ionic, and that is such, and must be covalent. You know, there is a way to make this kind of a judgment. Now this is good enough, all right, this is good enough, so we don't need this anymore. We will find the difference of the value of electronegativity from different elements, the difference between different elements, their value of electronegativity, play a role of making a bonding either ionic or covalent. So basically, if we consider we consider this is the character for ionic, right? This is let's say that's 100%. Of course, 100% is not possible, close to 100%. And here's ionic character getting 100%. Now down here is lower, right? Lower is not 100%, right? Almost also getting down here with 0. So now this y-axis is ionic characteristic of the bonding getting closer to 100%, point up. But here we have 1, 2, 3. All right, what is that? That's the delta chi. Delta chi is what? The difference of electronegativity. Take this off. Negativity. That's delta chi, right? Now what happened is we find this, the ionic character getting more and more when the value of what? The difference between two elements, the two atoms from two elements or one element is getting bigger and bigger, more iron. So this line is supposed to be going high. But then you have this, I think this is going to look like this. Alright? Now, when you're getting close to 1, the difference, the delta chi is getting close to 1, 1, 2, 3, alright? Into 1, and then we consider it's getting less than 1, it's going to be more close to here, right? This is what? This is more covalent, right? More covalent on this side, right? Covalent. The ionic right here, that's ionic. 100%, right? And then if you're getting 2, and then the difference is about 2 or more, right? 2 or more, you're getting more ionic, right? Or more ionic. So if we can make this kind of judgment, for instance, between sodium chloride 0.9 and 3, that's 2.1. 2.1 right there in the here. So this is start from what? Ionic, right? Ionic nature, right? Ionic nature. Here is more covalent. Covalent nature. Under 1, right? Basically under 1. So it's going to be something right here, not including 1. Here is close to not 1. So that is the case. Now, this tells us if we try to figure out the character of the bonding, either is ionic or covalent, right? Ionic covalent. I don't think this is going to be dark enough for my notes. Let me redo it. A little bit thicker. Right? Alright, so in between here is what? In this region, let's make a dot line here. Right? This region we call what? Hold on. Covalent. This region up to here. Right. Right. Now you can make a judgment, right, by using this feature and of the diagram, and then now so far we are done almost everything we should say about a relationship between the bonding polarity and the value of electronegativity, or the difference of a value of electronegativity from two atoms, either same or different elements, right? But that's how we can use that to judge the bonding nature, the nature of character. Now here, something else. I think we finished this electronegativity. This is going to be very useful in the future. We learn how to figure out the bonding polarity as well as the shape of molecules, right, with different bonding electron and non-bonding electron called it's a lone pair, right, lone pair electron. But here we have enough already, but before we erase that, I try to point out, if we try to find the trend of electronegativity, right? Trend, what is a trend? Like we already talked about a couple of different trends, right? A trend of oxidation states that we talked about, right? On the periodic table, go by their families, right? +1, +2, skip the B, +3, +4, +5, +6, +7, 0, and from carbons, -4, nitrogen -3, and -2 oxygen, and -1 for hydrogen, and that whole number line, that's a trend. I try to figure that out as well, but here it doesn't give you this kind of trend, but give you a tendency, right? A tendency. It's not necessary periodicity, but it's this periodicity. You go from the left of the period. The value of electronegativities for each different elements, one by one, getting greater and greater, slightly greater and greater, right? But if you go down, or you go from the bottom for each family, the value of electronegativity goes up, right? 0.7, 0.8, 0.91, 2.1, right? 2 point right here. 2.1. And the same thing for halogen, 2.5, 2.3, 4.1, right? So they both, this go up is going by column, family, go right, from left to right is going to increase, and they go from the bottom to the top, along the family column is getting increased. So you have both increase like this. Now, what is the total trend? The total effect, combined effect. Now, treat this as vectors. V-E-C-T-O-R-S, vectors. Now, vectors, by understanding this vector concept, by using a concept, a common sense we call slingshot. If you consider this is a rubber band, this another rubber band, you put a rock in the middle, here's a small rock right here, and then you pull the rubber band this way on the slingshot, where the rock goes. Does the rock go to one finger of you? Oh no, one side of it, that's my finger, the slingshot. Does the rock go to my thumb or go to my forefinger? No, it doesn't go either one of these. It goes in the middle, correct? You shoot in the middle. So, the same thing, shoot in the middle. So you have a trend of the electronegativity on the periodic table of elements. Has a trend of what? Diagonally. Diagonal. See what? I put a big arrow, horizontal. Oh no, the hollow arrow. Hollow arrow right here.